Okay, so I am recording. Yeah. Why does my voice always sound so feminine? I'm recording. I gotta do anything, you know. Musical routine. Okay, so this is the fourth session, and what I've done is on the website I've added some new documents, and these documents are actually from my PhD thesis from 20 years ago, something like that. And there's summaries of how I presented the data for when I did some serious regression analyses. So I've given you, I think, 3 documents. One is an overall summary of how my data was prepared and presented. You may want to follow a similar format for your thesis if you want to be really thorough and anal and really, you know, and hit the examiners over the head with just how much you care about your analyses. The other one, I gave you 2 more. The other one is a summary of how I identified interaction terms, and another one on how I identified confounding terms. And we're going to go through those today, because I'm so glad Megan's not here, because that's going to be one of the issues that she cared about for her thesis a lot. Just make sure I'm recording. I believe I'm recording. Excellent. So today we're looking at interaction terms, confounding expressions, and collinearity. And these are the great bugaboos, the great errors that get in the way of interpreting your results. So we're going to assume that up till now, you're able to create a logistic regression model, right? You've got your outcome, which is 2 levels, and you have your series of predictor variables, each one with a coefficient in front of it, and that coefficient represents the base E logarithm of the odds ratio, okay? But now we have to understand that these variables interact with each other in such a way that it prevents you from fully understanding the outcome. We'll go through examples and hopefully they'll make them more clear. So last time, if you weren't here last time, it's a shame because that was pretty intense last time. We covered the tests of significance and we went through 6 of them. Some were easier than others. The omnibus test was just looking at whether or not each block was significantly different from the block before. For those of you who are going to do just the single entry approach, I always sound so dirty when I say that. Single entry approach. And of course, the backwards entry isn't any better, but there it is. So both of them sound problematic. But the single entry approach, it's you obviously dump all the variables in at once and you run it and they're all there. That's fine. For that one, there's only 1 block. And the omnibus approach compares it to just having a constant. So a constant versus all the variables and test whether or not they're statistically different. Of course they'll be different. If they're not different, you're really in trouble. It means that your variables explain nothing. And you give up getting your thesis at that point. But it won't be that way because it almost never is. I can't imagine a scenario, even randomly, where that would be the case. But you never know. I mentioned that you can, the classification table, you could compute sensitivities and specificities, and those are simple things to do. I recommend you do them anyway because just look up the formulas and the data's there from the output, so you can make some commentary on the nature of the ability of each of your variables to be sensitive to predicting the outcome. That's what you're really saying, right? The R-squared we talked about a little bit. These are actually what are called pseudo R-squareds. So there are 2 outputs that SPSS makes. I never remember the names. I think one is Cox and Snell. The other is a Russian name that I've forgotten already. The Russian name is the more accurate one. But even the Cox and Snell is not a true R-squared. So if you remember your basic statistics, an R-squared is the measure of the percentage of variation in the dependent variable that your model explains. So the higher the R-squared, the better. The closer to 1, the better. Right? And SPSS will produce for you a pseudo R-squared. It's good enough. It's fine. So you want high. That's good. The minus 2LL, the log likelihood change, really is, for the statistical experts, that's what they will go to look at the quality of your model. And that's really a change in what's called the deviance scores. If it's difficult to understand, I would say don't bother with it. Because again, you're not going to be experts in regression. You're doing a simple master's degree, you're doing 1 regression, 1 or 2 for most of your theses, and just rely upon the other measurements if this one really gives you a hard time. If you're really adventurous, you want to get deep into the woods, then do some reading on the log likelihood change and see what you can do. And I say that because really, for me, the best measurement of significance is the Hosmer and Lemon-Show test. And for that one, you want to fail the test. So a non-significant result tells you that your model is good. So it's the only one where you want the p-value to be high. You want it because it's really testing to see if your model is as expected, for lack of a better word. Then we have the classification plot, and I mentioned that for that one you want a U-shaped curve, right? So you want it to appear as if the expected values are like this. And if it's not like that, then you have to investigate to see whether or not you're missing an important predictive variable that you should be in your model. And lastly is a case-wise list, where you look to see if any of the cases, which are the lines, horizontal lines in SPSS, if any of them are extreme outliers. And the output will tell you that, and you can actually set what your threshold for outlier is. If you're getting weird results, if you're not getting a significant model, then the case-wise list is probably where you're going to save your ass. Because you go through there and find the ones that are really giving you problems, and you kind of hold your nose and you delete them, and you make a note in your appendix, say, I deleted these because they were, clearly they're outliers that weren't representative of the fact that we're measuring. Make up some story. I can't believe I recorded that, but make up some story. But the justification is they're statistical outliers. And when they're gone, you're going to get a much tighter model that satisfies most of your case. Try not to delete more than a couple, right? You probably won't have to delete any, but in case things are really falling apart, you may have to delete a couple. So those are significance tests. And really, if you do that sort of thing, the examiners will be impressed because it shows you've got a robust understanding of the statistics and you've tested your model and it's valid, or at least more valid than it would be otherwise. Right, so like I said, I've added some new resources to the website, and these are all from my PhD thesis. One is a full analysis breakdown. So if you're looking for a way to present your data, or at least present what you've done, look at that. It's a thick appendix. It gives you some more thickness to your thesis, if nothing else. And then the last two we're going to look at right now. Okay, first we're going to define what a confounder is. Do you guys know what a confounder is? What is it?
Well, it's like it's not what you're testing for, but it can have an influence on the outcome.
Exactly, but it has an influence in a very specific way. Either it's preventing you from seeing a real relationship, or it's creating the illusion of a relationship. Right? And the confounder is what we're always afraid of. The thing about a regression, though, is that it automatically accounts for confounders. Because I mentioned that you're holding everything constant and testing each one, so you're holding the confounder constant too. And so it shouldn't have an effect at all. It's only relevant in this discussion if you're doing the forwards or the backwards selection method. Because the forwards and backwards selection method may take out some variables. At the end of the day, you may end up with fewer variables than you started with, because the process will say that, these other variables here weren't adding any quality or predictive value to your model, so we don't like that. Most statisticians prefer the forward and backward selection method because it creates a tighter, more, what's the word I'm looking for, attractive model. We all like attractive models. Tough crowd. So Zahar writes that down. We all like attractive models. So, but anyway, so if it's removing variables here and there, then you may remove one that's a confounder, and sometimes you kind of have to have it there to account for other relationships. Right. So that's a confounder. If you're having trouble understanding what a confounder is, think of it this way: it's separate from the relationship between the risk factor, which is the exposure, and the outcome. So in the case of the example we've been using all along, risk factor would be if we're modeling factors that are predictive of whether or not a candidate gets elected in an election, right? So the outcome is elected, yes or no, right? 2 levels, right? And a risk factor would be, are you male, yes or no? Okay, so a confounder might be, are you rich? So rich people are more likely to be educated and rich people are more likely to be male also. So what we're seeing here isn't really that being male gets you elected, it's being rich that gets you elected. So in that case, it's creating an association that's not really there. Another example would be, let's say you're doing a study in a public school, and you're trying to see whether or not being in English class versus being in woodworking class or shop class is more associated with having lung issues. And you find that, yeah, in fact, the students in the shop class have far more higher rates of asthma than students in the English class. And you conclude, maybe you conclude there's something about that room that actually is causing them to have asthma more than the English room. Maybe it's the dust in the air, maybe it's all this stuff. But what's really happening? What do you think? Yeah,
Maybe people in the English class are not exposed to the same type of...
No, that's what you're assuming. There's something else going on here.
Their personalities could be different.
Okay, personalities that affects that cause them to do what?
Different behaviors.
What behavior in particular? Smoking, exactly. So the kids in shop class smoke more in English class. So it's the smoking that's causing the asthma, not being in those rooms.
But aren't you assuming that those kids are smoking? What if they're not smoking?
Well, we have to investigate. So in the example I'm giving you, which is entirely hypothetical, I've investigated.
Okay.
And I find that the proportion of smokers is much higher in the shop class than English class. Right. So in that case, that's my relationship that I've perceived, but the confounder is smoking, which is a classic confounder. So here are the other classic confounders: age, sex, and socioeconomic status. They tend to always either create an illusion of a relationship or hide a real relationship, which is why in a regression analysis, you should try your best to have these factors in there. Not always. I mean, thinking of Peter's project, which is about, concussions or not concussions, age is related to concussion, sex maybe. Are you rich or not? Not really. I can't see that's going to have an effect. Smoking status, not really. But usually for population studies, these are critical. And the way that we account for them in a non-regression environment is we break down the data or stratify the data. So let's say sex is going to be our example. I got a good example for sex in a second. I'll tell you right now because it's my favorite one. So let's say we're doing a study on pregnancy rates in university students, depending upon which faculty you're in. We find that the students in the nursing faculty are getting pregnant like 1,000 times more than the students in the engineering faculty. Wow, there's something about studying nursing that gets you pregnant, or there's something about engineering that prevents you from getting pregnant. What's really happening?
There's more girls.
Exactly. Girls in nursing class, right? So the way we would analyze that then is that we take out the men and the women. Obviously, the men aren't going to get pregnant, so that's not a good example. So let's say the outcome was going to be breathing problems again. So, let's go back to the high school example. So we've got the shop class and the English class, breathing problems, no breathing problems. The confounder is smoking. So we take out the smokers and the non-smokers. We look at just the smokers and we say, for amongst the smokers, if you're in English class versus shop class, are you more likely to have breathing problems? Amongst the non-smokers, if you're in English class versus shop class, are you more likely to have breathing problems? And that accounts for the confounding. So we call that breaking it down by the variable or stratifying. So which leads me to the only epidemiology joke I know. Ready? That is, what is an epidemiologist? Someone who's broken down by age and sex. Huh? Yeah?
It's broken down
by age and sex. No. Maybe I'll lose something in the translation. All right. Tough crowd. All right. There it is. It was stratified by those variables. So there's the example I just gave you, the example of engineering students and nursing students. So confounders are the big thing we always care about. So other thing to consider with confounders is they are not in the causal pathway. That is, they are separate from the relationship. So in the case of the shop class and the breathing problems, it's not that the mechanism by which the shop students were having breathing problems was the smoking. It's the smoking was masking that association. So another example is this. Here we have diet and heart disease. So it's showing that maybe what you eat is more likely to cause you heart disease. If you eat like lots of butter, a lot of fat products, you have a higher rate of heart disease. That's great. Cholesterol is not a confounder. Cholesterol is the pathway by which the fat gives you heart disease. Right? So it's only a confounder if it's not part of that pathway, if it's separate entirely. Get that clear? Now in this case, and this is in a regression analysis, if we had diet and cholesterol together in your regression, that's a different kind of problem because they're measuring the same thing. And they're going to increase together and decrease together. We call that collinearity. And I'll show you that in a second, how we deal with that. So we have to be aware of collinear variables also, because they will sort of increase the amount of error in your model. Another example of collinearity is, let's say you've got two measurements of height in your studies. You've got height in inches and height in centimeters. They're two different variables in your data set, but they're measuring the same thing. If you graph them, they're parallel to each other. It adds nothing to your model, it just increases the error. So we want to avoid that. Okay, so there's lots of ways of detecting confounders. I'm only going to show you one of them, but there's a lot of subjectiveness to this. So I'm fond of saying so many times that the computer only does so much. The computer is dumb. It just crunches the number. It comes down to your intellect, your brain power, to decide what is likely a confounder. To test for a confounder, you pretty much have to have in mind a primary explanatory variable. What is that? A primary explanatory variable is one of the variables in your long list of risk factors that you care about the most. So, what's your prize again, Sarah?
HIV, yes or no.
And what's it modeled against?
Oh, so many things. One of them, some of them are the age 6, like that.
Okay, so your research question, maybe you care about something more than others. Maybe you care about whether or not they're refugees.
Oh, but female is educated or not.
Okay, there it is. So you're a perfect example.
Yeah.
So education is your primary, your principal research, your primary explanatory variable. So you care about things that affect the relationship between that variable and HIV status. So that's good. That's the first thing. What we're going to do to test it out is you're going to create a logistic regression model, doing everything we've done so far. Then you're going to look at the beta value, the coefficient of that primary explanatory variable. Remember what it is. Then you're going to take out one of your other variables, run the whole regression again, look at how much the beta value has changed. Put it back in, take out another one, run it again, look how much it's changed. Take out another one, run it again, look how much it's changed. So you got to test each one in turn and see how much the coefficient of your primary explanatory variable changes. And I will say, if it changes 10% or more, then the variable that you took out is probably a confounder. Right? Why that? Because I use that reference here, Kleinbaum and Cooper from 1988. That's their method. There are other ways of doing it. This is not the easiest way, it's the most straightforward and easy to understand way. That's why I recommend it to you.
If an examiner asks me why 10%?
Because that's what Kleinbaum and Cooper said.
So I just cite them.
You just cite them.
Okay. I don't have to explain. I understand.
Exactly.
Yeah.
So you're just running a logistic regression for every single variable.
No. So you got all the variables together. Okay. Let's say, using her example. So here we've got HIV status, yes or no. Okay. And here we've got other factors. You've got, are they a refugee, the age, socioeconomic status, and education. Okay. So you run everything together. Now, for each of these variables, there's going to be a beta, like a coefficient.
Right.
Okay. So you remember the one for your primary risk factor. In her case, is education. That's what you care about most. So that's your beta. Put it over here. Okay. Now we're going to test each one of these other variables in turn. The first one, take it out.
Then
Run the whole thing again.
Okay, I got
Now
it.
look at this, the beta again. Now see how much it's changed from where it was before. Then put this back in. Take out this one. Run it again. And see how much this has changed again. Right. So most of them aren't going to change much. The one that changes it a lot is probably your confounder. Now let's say you do that. Here's an example. So this is from my PhD. And I gave you just 4 examples from like 30 variables. So in this case, my outcome is whether or not these women got pregnant, yes or no. And I've got all these other variables. The first one is their cause of infertility. Second one is whether or not it was done after a certain date. third one is whether or not the eggs are frozen, for all these things. Okay? And what I care about the most is the number of embryos that was transferred. That's further down the list. You'll see that. So in that first column is the coefficient when everyone was together for the principal primary variable that I cared about. Here it's 0.679. Now remember that's coefficient means, right? If I take e to that coefficient, that gives me the odds ratio. I don't care about that right now. The next column tells me how much that has changed when each of those variables was removed, right? And the third one, I compute the percent difference. So I just, take the difference and divide it by the first one. First one changed by 2%, second one 1%, 6%, that's pretty high, right? But down this one here, 11%, so that's why I've got that bolded. 11% number of oocytes divided in my sample. So that one is my confounder. What do I do with it? I was using a backward selection regression. So a backward selection regression, some of these will be taken out by the computer because the computer decides that they're not important. They're not changing the model enough to warrant staying in. So in that case, I got to go back and force that one in. I have to force that confounder back in because it's clearly playing some kind of role I need to be accounted for. If I didn't force it in, then the relationships that I'm seeing in my model may in fact be affected by that variable. Because even though it's not in the model, it's still affecting the data. The data's there. So as long as it's in the model, the computer can account for it. Now, if you're using the forced entry approach, I'm saying that, the forced entry approach, you probably don't need to do that unless the computer has, for some reason, taken it out. Because sometimes it will take it out if it's saying this has no relevance to me. And SPSS will allow you to force things back in. So that's why you're doing this, to figure out what to force back in. Okay. That's confounding. Any questions on confounding? It's pretty straightforward. Collinearity we talked about a little bit. So collinearity is when these things are essentially measuring the same thing. The obvious example was, again, height in inches and height in feet in the same model. Or if you got education and SES, that could be a problem, right? Because SES, socioeconomic status, is a combination of education, income, and social class. So that's very commonly a multicollinear issue. And the problem with having things in your model that are collinear is it increases the error by a lot. So we want to reduce that. So there are lots of ways of accounting for collinearity. The best way is to run something called a variance inflation factor. But I'm not going to tell you to do that, because you're not statisticians. If you want to play with the VIF, you can do that. And the way you do it in SPSS is you don't run a logistic regression, you run a linear regression. And it allows you to select a VIF estimate. But I'm saying don't bother, because that just confuses the matter. There's an easier way to do it that probably gives you similar results. And the easier way is to run a correlation matrix. Now, what is that? This only applies for your continuous variables, things like age and weight. You remember what continuous means, right? We've covered that. Right? If it's not continuous, it's possible to have collinearity, but in my experience, it's not as important. So again, to save you some time and effort, I would say don't bother with the categorical variables, just test the continuous ones. The reason for that is most of the time with the categorical variables, it has to do with different levels in that category are collinear, and that means nothing. So in the case of things like age and weight, maybe economic status, anything that you have identified as being continuous. Now remember, in logistic regression, sometimes we pretend that ordinal variables are also continuous, right? Like number of rooms in the house, number of children you have. Those are ordinal, but we code them as continuous. So that counts for this as well. So a correlation matrix looks something like this. Yes?
Oh, what if it's males and females? Like if we say males are not as educated as women.
Well, there are two variables there. There's education and there's gender.
Yeah, and gender is not it's categorical.
Right, so don't bother gender. But in your soup you have SES.
Yeah. So
all we care about are the continuous variables. So maybe SES is correlated with age. Maybe it's correlated with weight. Who knows?
So I just forget about the...
That's right. Yeah. So the way you run, and I recommend using Spearman's coefficient. There are lots of correlation coefficients. Again, it's not a stats class, so I'm not going to go into deep them, but the two main ones are Pearson's and Spearman's. Pearson is a real correlation coefficient. Spearman is a ranked correlation coefficient. What does that mean? The short answer is that Pearson's correlation coefficient looks at whether or not, let's say you're looking at whether or not age and height are correlated. Because both are continuous variables. One's measured in years, one measured in centimeters. Pearson's correlation coefficient looks at whether or not if I plot the two, I get a straight line. Spearman's looks at whether or not if I plot the two, I get what's called a monotonic relationship. So if I draw it this way with you, let's say this is a height and this is age. That's a straight line. This would be a monotonic relationship. It's not always straight, but it's always going in the same direction. Right? So Spearman's is a little more forgiving for nonlinear relationships. That's why I recommend using Spearman's for this. You'll probably get the same answer for most cases anyway, to be honest. But SPSS, you can easily run a correlation matrix. Just select all these variables, select correlation, and it'll give you an option to check off which one you want. Check off Spearman's. And if you've never seen a correlation matrix before, here are the variables. Here are the same variables. I just label them A, B, C, D because I don't want to repeat my text. So everything on top here is the same as down here. It's a mirror image. So we just look at one of them. Look at this one here, for example. So here we've got the actual number of the correlation, and this is the p-value. For correlations, the p-values don't really matter. Okay? The p-values are really testing, is it different from 0? We don't care about that. What we care about is the actual coefficient size. The closer to 1, the more correlated it is. We don't want it to be correlated. So, in general, we say if it's 0.8 or above, it's really, really collinear. Ideally, if they're really collinear, think about taking one out. So, if you've got two measurements, cholesterol level and butter intake, okay, and they're really collinear, like 0.8 or above, take out butter or something like that. Just don't even bother with it. And explain in your appendix that this is removed for collinear reasons. But if you're convinced intellectually that they have to stay in, then we're going to treat them as if they are interaction terms. We'll talk about interaction terms in a second. But the best thing to do if they're really high is to take one out. Now, if it's not high, if it's just moderately high, like 0.4 or something, we're going to pretend that they're interaction terms. We'll get to that next. That's collinearity. So collinearity, this is the biggest problem with regressions in general. Regressions are great for confounders, they're crap for collinearity, because a lot of things are collinear. Right. So what's an interaction term? You'll hear this phrase a lot, interaction term or effect modifier. They mean, okay, different people will say they don't mean the same thing. In my world, they mean the same thing. So when I say either one of these two, I'm talking about the same thing. So a confounder, if you remember, either created the illusion of a relationship or it hid a real relationship. An interaction term is not the same thing. What an interaction term does is it prevents you from appreciating the direction of the relationship, or it changes the direction of a relationship. So the relationship is real. There's no illusion going on here. In the case of maybe it's being in shop class does give you more breathing problems. It's real. An interaction term will change whether or not it gives you more breathing problems versus less breathing problems. Give me an example. Okay, so important here is it doesn't mask or create a relationship, it changes the direction of the relationship. And this is good for you because if you find the interaction term, it's a fun thing to graph. It's a fun thing to show in your thesis. Because, oh, look at all the work I've done here. This is great. Right. Here's an example. So let's say we're looking at the relationship between joint mobility and exercise. So the more you exercise, the more mobile your joints are. That's obvious. Okay. So here is mobility. Here is exercise, right? So exercising more, my mobility increases. That's great. But let's say I'm old. Let's say I'm over 65. What happens now? The more exercise, the less mobile my joints get because I got arthritis. right? So clearly the relationship is real. It just goes in a different direction. So something has modified the effect, an effect modifier. What variable has modified the effect? Age, exactly. So in this case, age is not a confounder, it's an effect modifier, right? There it is. So this is from my thesis again. So one of the ways I presented the data, so here is this thing called indirect cryopreservation. So I dealt with fertilized eggs, human eggs, and we looked at whether or not if you've got this quality of egg going this way, this number of eggs divided, the probability that they were good for becoming pregnant with. We found that as the quality increased, that the more likely they were, so the quality increased, the less likely they were to be good for pregnancy. However, if they were frozen, they got better. So in this case, the freezing of the egg changed the direction of the relationship. So the freezing was an effect modifier, interaction term. Right? And if I didn't know that, then this would really screw up the entire relationship that I'm modeling here. So what you can do if you find an effect modifier is make one of these graphs. It looks so cool, right? It's really unusual to get a cross like that. That's like perfect almost, right? That's pretty cool. And that's a publisher result in and of itself. That is a paper by itself. You find an interaction term. So there are different kinds of interaction terms. You can say they're added together. So maybe age plus sex is changing things. Maybe age times sex is changing things. Or maybe age times sex times income is changing things. There are different ways of combining these variables to show the interaction term. But really, that's the usual scenario. You've got two things interacting and they're multiplied. And I would say don't even bother looking for the other two, especially for the studies that you're doing and at your level right now. Just assume that there's two variables and they're multiplied. So, right, so I'll show that in a second. Okay, so there are lots of ways to detect interaction term, but the easiest way is, first, a lot like the confounding, use your intellect. So is it likely that sex and SES are interacting? Sounds like it, right? So that's something you should test. Is it likely that maybe age and smoking are interacting, where older people are likely to smoke and younger people are? Maybe. That's something to test out. Or you go back to that table we just made, right? This table over here. This one here, right? And look to see, are there any of these that are high that we didn't toss out? Like none of these are high. All these are quite low, so I didn't toss any of them. But this guy here, that's getting close. It's almost half, right? So my rule, this one, there it is. So my rule of thumb is if it's 0.5 or above, then I think that's worthy of exploring to see if it's interacting. In this case, it would be this one here is interacting with this one here. So C, right? So this one is interacting with that one, creating that number there. Okay. And really, if it's a really strong interactor, it's going to be so glaringly obvious. But if it's a weak one, then you mess around with it. If it's a weak one, it's not going to change your model that much. But if it's a strong one, you want to find it. Okay, so go ahead. Okay, right. So again, so you check the table, you go through your intellect to see which ones are likely interacting. Now, this is what you're going to do. You're going to create an interaction term by multiplying out those two things. Right? So in this case here, I showed you the estradiol and variable C and D were interacting. I'm going to create a new variable where I just multiply those two. That's all it is. And that's my interaction term, I call it. And I put that in my logistic regression model, and I see if it's significant. So let's see what that looks like. Here it is. So when I did it in my thesis, I created all of these interaction terms. Actually, the list goes on and on. Okay? So, and then I put them in my logistic regression model, and I saw if it's significant. And this one was. So this one stayed. The rest of them I took out. That's all it is. Just dump them all in there and see which one's significant. So it's possible to do a fishing expedition. You can just randomly throw in all the combinations you can think of and see what the computer says is significant. That's not elegant, and it may cause some issues, right? It's not defensible. This strategy is defensible. It says, I looked at collinearity, I looked at what the literature suggested is probably happening, and I threw these terms in here. So I'll repeat myself. All you do is you take these two variables from your data set, you create a new one. Use the compute variable function, SPSS I think it is, and just say new variable equals this times that. Done. And add that to your variable list in your regression. That's all it is. Now there's a nuance here. And that is that if this goes in and stays in, then both of these must go in and stay in. Right? So like I said, the computer wants to toss out things that aren't relevant. Maybe it tosses out this variable here. Okay? But this stays in. It doesn't make any sense for a variable made up of two other variables to stay in when one of them is gone. So if this goes in, you got to make sure these two are forced in. When you interpret it, at the end of the day, this doesn't get interpreted. Some people can interpret, the odds ratio means this and that. I wouldn't bother interpreting it, just leave it there as a thing. Okay, so keep it in the model, and you got to make sure that both of these stay in as well. Whew, wow, that's the last slide. Okay. Is that clear a little bit? I mean, it won't be that clear until you try it out yourself. I've really got it down to a recipe here for you. It's a little more complicated than this, but this is probably good enough to run your analyses and to satisfy your examiners, right? So I think we'll have one more session, and the next time it'll be after reading week, assuming I come back from the occupied territories. And what we'll do is hopefully you have a chance to try this stuff out, and we'll go through the list of all the things you have to do again and review it all and see where maybe we're having troubles. Sounds good? Yeah. Right on. Yay! It's been fun.